Hi everyone, so we're going to be going over chapter 2.6, which is transformations of functions now. So this section is going to be very foundational in the sense that it does pop up later on in the course, just transforming different functions like exponential functions and logarithmic functions that we'll learn about later. So it's just a good skill and important material to know from this section. So transformations are considered as shifting, reflecting, stretching, or shrinking of graphs. So we're going to go over those and how to recognize them. And also you could do those vertically or like through the y-axis and horizontally, which is like through the x-axis. So first we're going to do vertical shifts of graph. So we're going to say that c is just going to be some constant that's greater than 0, and f is going to be our function. So if we have f of x, y equals f of x plus c is going to be the graph of y equals f of x shifted vertically upwards c units. So we can see that we have our f of x, or our y value, and we're adding c to it, which is going to be, since we're adding, we're shifting vertically up c units. The graph of y equals f of x minus c is the graph of y equals f of x shifted vertically down c units. So here's a little picture of what's going on. So the blue is our original y equals f of x graph. And by adding c, we're shifting up. And that's the red graph, c units. So that difference is c. And then on the right, we're subtracting c. So we're shifting down c units. So here in our example, I have g of x equals x squared plus 3, h of x equals x squared minus 2, and I just put the g of x in. I don't know. We can just get rid of this one. Then I'll just change the color so it could match our graph. So this one's the red. And then this one's purple. Alright, cool. So we have g of x equals x squared plus 3 and h of x equals x squared minus 2. So here we have f of x equals x squared. So this is actually known as like the parent function, or like our original function before the transformations. So usually the parent function is going to be a pretty common function, or your bare bones function that you'll be able to recognize. So we have f of x equals x squared. That's our parent function. G of x, we're adding 3. So x squared is like the f of x. So we're adding 3. That's our c. So we shift up 3 units. And then h of x is x squared minus 2. So that minus 2 is shifting down 2 units. So the shift up is 1, 2, 3 units. The shift down is 1, 2 units. Okay, in our next example, we have use f of x equals absolute value of x. So that's our parent function. To obtain g of x equals the absolute value of x minus 4. So here we have f of x equals the absolute value of x. So I'm just going to plot some of those points from the original function. So I'm just going to have 0, 0, 4, 4, because the absolute value of 4 is just 4. And then negative 4, the absolute value of negative 4 is 4. So I have these 3 points that I obtained from the parent function. And I'm going to apply transformations to those points to get points from g of x equals absolute value of x minus 4. So instead of just like choosing random points to plug in to g of x to get our y values, I'm going to use the points from the parent function to get our values. So minus 4, and this is a vertical shift down. So I'm vertically shifting down 4 units. So I'm going to actually subtract 4 from each y value from our f of x. So let's start with 0, 0. So if I subtract 4 from 0, I get negative 4. So our x value stays the same. But our y value now is negative 4, so that's this point. And then now I'm going to do 4, 4. So I'm going to subtract 4 from 4, our y value. So this gives me 0. So now I have 4, 0. That's this point. And then I have negative 4, 4. I'm going to subtract 4, and I get negative 4, 0. So that's our new graph. So here, and then also on quizzes and tests, I don't want you to be just plugging in random values to find the g of x. It's a lot easier, and it's also the way I want you guys to do these problems, is using parent function values or points and then applying the transformation to get the new points. Okay, horizontal shifts of graphs. Okay, this one's a little bit tricky or weird, but I'll explain that right now. So suppose that c is greater than 0 and f is a function. The graph of y equals fx minus c is the graph of y equals fx shifted right c units. The graph of y equals fx plus c is the graph of f of x shifted left c units. So you might think, that's kind of weird. Like, if it's x minus c, wouldn't the minus imply that we're like shifting left, and then the x plus c imply that we're shifting right? That's kind of like intuitively what we would think, but it's actually the opposite. So a way that I like to think about it is think about the point x equals 0. So say that was our original point, and we have f of x plus 3. So in order to get back to our original point, so say I have some x value in here, and I'm adding 3 to it, but I want to think about how to get back to x equals 0. That is, I'm going to do, like, what x value can I plug in here that when I add 3 to it, I'm going to get back to 0. And that's going to be negative 3. So that's a shift left by 3. So I have negative 3 plus 3 equals 0. So this minus 3 is like the shift left, because negative 3 plus 3 is going to get me back to the 0 value. Okay. And then if that still doesn't make sense, you could always come during office hours and I can explain it to you. And then also, I believe it's purplemath.com. They have excellent resources about like transformations of functions, and they give like a pretty good explanation on this shifting business here. But basically, the important thing to remember is if you have x minus c, you're going to be shifting right. And then if you have x plus c, you're going to be shifting left c units. So here we have our y equals f of x, the pictures, and then if I have f of x plus c, that's going to be a shift left. And then I have y equals f of x, and then the c is going to be the y equals f x minus c, and I'm shifting right in this case. Okay, so in this example, we have f of x equals square root x, and we're wanting to obtain g of x equals square root x plus 5. So we know that f of x equals square root x is our parent function. So as we can see, the horizontal shift is when it's like inside the x or inside our function. Here is how we know the difference between a horizontal and like a vertical shift, because the vertical is going to be outside the function. So as we're inside our function here, we could tell that this is a horizontal shift. So I have that y equals g of x. It really is as square root x plus 5, which is really, if we had like f of x plus 5, then we would be plugging in the x plus 5 into the x value, which is how we know we have a horizontal shift here. Okay, so I have points from our original function. So I have 0, square root 0, 0. So I have that. I have 1, 1 because the square root of 1 is 1. And then for 4, the square root of 4 is 2. So these are points from my original function here. And I'm going to use translations to get points for my new function, g of x. So I'm going to shift 5 units left because our function is x plus 5. So I'm going to be subtracting 5 from each x coordinate because it's a horizontal shift, because we're moving left and right and not up and down. So I'm going to start with 0, 0. So I subtract 5 from that coordinate and I get negative 5, 0. So the 0, the y value stays the same, the x value changes. Now 1, 1, I subtract 5 from 1 and I get negative 4. So I have negative 4, 1 now. And then for 4, 2, I subtract 5 from 4 and I get negative 1, 2. So that's my new points for my g of x. Okay. In this example, I'm going to be combining horizontal and vertical shifts. So I'm going to use f of x equals x squared, and that's our parent function, and we want to obtain h of x equals x plus 1 squared minus 3. So the x plus 1, that's our horizontal shift, and then the minus 3 is the vertical shift. So first, I have my parent function. So I have points for my parent function, and that's going to be the f of x equals x squared. And I have 0, 0. And then I have 2, 4. And then negative 2, 4, because our parent function is x squared. So those are just points that I just chose. And then now we're going to apply our horizontal shift. And that since we have x plus 1 squared, that's 1 unit left. So I'm going to subtract 1 from each x coordinate. So I could go ahead and I'll just start with 0, 0. And so I'm going to subtract 1 from 0. So I get negative 1, 0. Subtract 1 from negative 2, negative 3, 4. And then 1 from 2, I get 1, 4. So now I have the function g of x equals x plus 1 squared. But remember, now we have to do our vertical shift. So we'll go ahead and do that. And that's our third step. So I'm going to subtract 3 because it's a vertical. So I'm going to shift g vertically down 3 units. So I'm going to subtract 3 from each y coordinate. So I have 4, 0, and 4 are my y coordinates. So now I keep the x coordinate and then I'm just dealing with the y coordinate. So I have negative 3, 1, because I'm subtracting 3 from 4. I have negative 1, negative 3, and 1, 1. So that's my function. I have x plus 1 squared minus 3. So we're good to go. Okay, now I'm going to talk about reflections. about the x-axis and then the y-axis. So I have the graph y equals negative f of x is the graph of fx reflected about the x-axis, sorry. And then the graph of y equals f of negative x is the graph of f of x reflected about the y-axis. So I like to think of it as like in these graphs here that I have. So when I am going to be changing the y value here, because I have the negative on the outside, so that's going to affect my y value. I have a negative f of x. So if I'm going to be changing the y value to negative, that's why I'm flipping over the x-axis here. So I'm going from up here to down here, so that's a flip over the x-axis. And then when the negative is the inside, I'm changing the x value. So here I have a positive x value, and then over here I have a negative x value. So that's changing, and I'm flipping over the y-axis. So that's how I like to remember it. Okay, so let's go ahead and do an example. So I have use f of x equals the cube root of x, so that's our parent function, to get g of x equals the negative square root 3 x, or g of x equals negative square or cube root 3 of x. Okay, so I'm going to start with the parent function, do some points from there. Okay, so I have I just have 0, 0, so that's like a pretty classic point. And then I have 8, 2, and then negative 8, negative 2. Because of the cube, I'm just doing the cube of the x values. So like the cube root of 8 is 2. And the cube root of 0 is 0, and cube root of negative 8 is negative 2. Okay, so my g of x is really, I could write it like this. It's a negative cube root of x. So the negative is on the outside, so I have negative f of x, so that's going to be a reflection about the x-axis. So I'm going to replace each y-coordinate with its opposite, or I'm going to negate it in order to flip it over the x-axis. So that's like here in this example. So I have negative 8, 2. I'm negating this value here. Then negate 0, 0, just 0, 0 again. Negate this one. And then I have 8, negative 2. Okay. Now I'm going to do f of x equals square root x to graph h of x equals square root of negative x. So since the negative's in the inside, this is similar to f of negative x. So I'm going to reflect f about the y-axis. So I'm just going to replace each x coordinate with its opposite. So I just have points for my parent function, 1, 1, 4, 2, just to start us off. I'm negating the x coordinate. So I'm going to have negative 1, 1, and negative 4, 2. Okay, now I'm going to go over vertically stretching and shrinking graphs. So let our s is going to be function and c is going to be positive real number, or just c is greater than 0. So, actually we don't have that because I break it up into cases. Okay, so if c is greater than 1, the graph of c of f of x, the c's on the outside because we're vertically stretching and shrinking, is the graph of y equals f of x vertically stretched by multiplying each of its y coordinates by c. So that's if c is greater than 0, or greater than 1, excuse me. So multiply each of its y coordinates by c. If c is between 0 and 1, so what does that mean? That means it's going to be a fraction, right? It's between 0 and 1. the graph of y equals c f of x is the graph y equals f of x vertically shrunk by a factor of c. So we have y equals c f of x. When c is greater than 1, we're vertically stretching the graph. So the blue is the original function, and then the red is we're stretching it by multiplying each of its y coordinates by c. And then if c is between 0 and 1, we're vertically shrinking it by a factor of c. So blue is the original, and then we're shrinking, so our red is the new function. Okay, so for example, we have f of x equals x cubed. To obtain h of x equals 1/2 x cubed. So the 1/2's on the outside, so that's going to be vertically. And since 1/2 is between 0 and 1, we're going to be vertically shrinking by a factor of c, by a factor of 1/2. So we multiply, or I have the parent function values, so I just did 2 cubed is 8, and then -2, -8. So I just did those 2 points. And we're going to be multiplying our y values by, or our y coordinate by a factor of c, which is 1/2. So I multiply my y's, so that's 8 and -8 by 1/2. So I get 2, 4, and then -2, -4. Alright, now we have horizontal stretching and shrinking. So this is also the tricky one with the stretching and the shrinking. It's usually the horizontal ones that are a little bit different. So again, we have f as a function and c is a positive real number. So if c is greater than 1, the graph of y equals fc of x is the graph of y equals f of x horizontally shrunk by dividing each x coordinate by c. And then if c is between 0 and 1, the graph of c of x is the graph y equals f of x horizontally stretched by dividing each x coordinate by c. Okay, so really the idea behind this is if c is greater than 1, then we're shrinking the graph of y equals f of x horizontally by a factor of 1 over c, which is the dividing each x coordinate by c. And then if c is between 0 and 1, that means c is a fraction. And we're stretching the graph of y equals f of x horizontally by a factor of 1 over c. So if you think about that, so if c is greater than 1, we're shrinking by dividing each x coordinate by c. So each x coordinate is going to get smaller. So we're shrinking the graph. So that's our first picture with our red. The red is the y equals f of c of x, because we're shrinking because our x values are getting smaller. Now, if you think of c being between 0 and 1, we have a fraction. And if we're stretching the graph by a factor of 1 over c, well, c is a fraction. So say c was 1/2. So we would really have, let me do 1 over c. If c was 1/2, we really have 1 over 1/2, which is really 2. So we're stretching the x coordinates by a factor of 2. So that's why it's stretching and it's expanding out. Okay, so for example, you have f of x, and I just have some points here. So we have 1, 0, and then 1, 1. And then if I have f of 1/2 of x, that means that the 1/2 is in the inside. And since c is 1/2, we're going to horizontally stretch by dividing each x coordinate by c. Or dividing, so I have 1 as an x coordinate. So really I have 1 over 1. I'm going to divide that coordinate by 1/2, which is the c. So dividing the x coordinate 1, by 1/2. And that becomes, the division becomes multiplication with fractions. So I really just turned 1 into 1 over 1 just because I knew it was going to be a fraction. So I have 1 over 1 times 2 over 1 now, which is 2. So now our 1, 0 coordinate is a 2, 0 coordinate. Alright. I'm going to make another video. It's going to be a supplementary video to this one. And it's just because I want to just tie everything all together. And so this is a little preview into that. So the order that transformations are performed, if you had a whole equation and say there was one of each transformation, you'd be performing the horizontal shifting first, then the stretching or shrinking, reflections, and then vertical shifting would be next. But I'm going to have a separate video for that just because it is hefty stuff. So I wanted to dedicate a single video to that. So I'll be doing that later. But I just want to go over even and odd functions really quickly. So an even function is if a function f satisfies the following relationship. So if I have f of negative x, say I had a function f of x, plug in negative x, and I simplified, and I got my original function back. I got f of x back. For every number x in its domain, then it's going to be an even function. So for example, if I have f of x equals x squared, this is even because I plug in negative x to f. So I have negative x squared. And remember, the parentheses is around the whole thing. So I have negative x squared. Really, the negative is like a -1, and I could distribute the squared to it. So I have -1 squared times x squared. It's just -1 squared is 1, so I just get x squared. So that's my f of x, my original function, so that's even. So even functions are symmetric with respect to the y-axis. That means that they're reflected across the y-axis. So, for example, let me just draw a quick picture here. You have your parabola. They're symmetric. So this side of the y-axis looks like this side of the y-axis. So that's what it means to be symmetric. So it's going to be odd functions. If a function f satisfies f of negative x equals negative f of x for every x in its domain. So I have my f of x, I plug in negative x, and I get negative whatever my original function was. So for example, I have x cubed is odd because if I plug in negative x, I get f of negative x equals negative x cubed. I'm going to cube the -1 and the x, and -1 cubed is still -1. So I have a negative x cubed. So that's negative f of x because the -1 is out here, and then the x cubed is my original function. So f of x equals x cubed is odd. Odd functions are symmetric about the origin. So if you graph x cubed, it's symmetric about the origin. This, it looks like this on the other side of the origin. So symmetric about the origin is equivalent to reflecting across the x-axis and then the y-axis. Okay, so for example, we're going to do a quick little example to see which functions are even, odd, or they could even be neither if it's not the original function or if it's not the negative version of my original function. So I have x to the 5th plus x. So I go ahead and plug in a negative x there. So I have negative x to the 5th plus negative x. I get negative x to the 5th minus x, which I could go ahead and factor out a negative. So I get negative x to the 5th plus x, which is negative f of x. So our f is odd. Okay, for b, I have g of negative x. Just plug in the negative x to see if it's even, odd, or neither. So I get 1 minus negative x to the 4th. So that's going to be 1 minus x to the 4th is just x to the 4th. I keep that minus sign there because I have a minus sign here, but then I'm plugging in a negative x. So remember, the parentheses go around the whole thing. So keep track of your negatives. So I have 1 minus x to the 4th, which equals g of x. So g is even. Now I have h of x is 2x minus x squared. Plug in negative x. So I get 2 negative x minus, because I have a minus there, and then parentheses around the negative x squared. So I get negative 2x minus x squared. So I'm going to factor out the negative. So I get 2x plus x squared. So I can see that h of negative x isn't equal to h of x, because that isn't 2x minus x squared. And h of negative x is also not equal to negative h of x, because this inside here, that's not h of x. That's not 2x minus x squared. So I have that h is neither even nor odd. Okay, so that's it. For this video, we just went over transformations and functions. It's going to be very useful and very important topic to know for this course. Again, I'm creating that other video to go over in-depth examples of tying everything all together, applying multiple transformations, and how the format that I'll typically use on exams and tests also when dealing with this kind of stuff. And then also our even and odd functions, another thing to know. So see you next time.